Large language models, they feel like magic, right? But what are they really? Let's cut through the hype. In this explainer, we're going to break down how they actually work, right from the ground up. And we're going to start with the most surprising part, what an LLM physically is on a computer. You're not going to believe this, but a massive, powerful model like Meta's Llama 2, the 70 billion parameter version, it all boils down to just 2 files. That's it. For something so incredibly capable, it's a shockingly simple package. So, okay, what are these 2 files, and how in the world do they work together to create something that can hold a conversation? That's the very first thing we need to wrap our heads around. Well, on one side, you have the parameters file, and for a model like Llama 2 70B, this thing is a monster, a colossal 140 gigabyte file. You can think of this as a model's entire brain, all of its knowledge. And on the other side, a surprisingly tiny file with only about 500 lines of C code. This is the engine, the simple logic that knows how to read that giant brain and make it talk. So here's the first big takeaway. Running an LLM is actually pretty simple from a coding perspective. The real magic, all the complexity, all the mind-boggling power, is packed into that enormous parameter file. Which, of course, leads to the next question, how on earth do you create a file like that? And that brings us to the forge, the process called pre-training. This is how that massive knowledge file gets created. You know, the best way to think about pre-training is like creating a lossy zip file of the internet. You're basically taking a giant slice of the web and compressing its very essence, all the facts, the concepts, the way we use language, into the model's parameters. It's not a perfect copy, of course. It's more like the gist of it all. Now, check out these numbers, because this is where you really start to feel the scale. To create that 140 gigabyte file, you start with 10 terabytes of text. Then you fire up 6,000 specialized, very expensive GPUs, and you run them flat out for 12 days straight. The price tag for that little experiment? About $2 million. We're talking about some serious real-world constraints here. And what is this multi-million-dollar computer melting process actually trying to do? Something so simple. It's just trying to get really, really good at predicting the next word in a sentence. That's it. But in forcing the model to get good at that one simple task, it has to learn grammar, facts, and even basic forms of reasoning. It all gets baked right into those parameters. So the takeaway is pretty clear. Pre-training is a massive brute force capital investment. It's wildly inefficient, but it's really good at one thing, creating this huge foundational knowledge base. But here's the problem. This new brain knows a lot, but it has no idea how to be helpful. It's just an internet dream. And that leads us to the next crucial stage. How do you take this raw, knowledgeable model and turn it into a useful, polished assistant that you can actually talk to? This is where fine-tuning comes in, and it's a completely different approach. If pre-training was all about getting knowledge by hoovering up a massive quantity of data at a huge cost, fine-tuning is all about teaching it behavior and alignment using a small amount of high-quality, human-made data. And it's way, way cheaper. It's a classic engineering trade-off. Do you want scale or do you want precision? The process itself is pretty straightforward. First, you have actual people write up thousands of examples of perfect conversations, good questions, and really helpful, safe answers. The model then trains on these to learn the assistant style. And then, sometimes you can go a step further. Have humans rank different AI answers to the same question. This helps it learn nuance, and that's a process called RLHF. So the key idea here is that fine-tuning is a much faster, cheaper, and more iterative process. It's like sending the model to finishing school. You're trading that raw data volume for high-quality examples to add that essential layer of safety and helpfulness, and really align it with what we want it to do. But today's LLMs are evolving beyond just being polite assistants. They're turning into something way more powerful, something that looks a lot like a new kind of operating system. To get what I mean, let's ask a simple question. We know an LLM's knowledge comes from pre-training, which happened in the past. Its knowledge is frozen. So, how could it possibly know the current valuation of a company like Scale AI? The short answer is it can't, not by itself anyway. And this is where the new paradigm just clicks into place. The LLM acts like an OS kernel. First, it recognizes the limits of its own knowledge. It basically says, hey, I need to look this up. So it sends out a command to use a tool like a web browser. It gets the search results back, realizes it needs to do some math, and then calls another tool like a calculator to process the data. And only then does it put everything together to give you a final answer. So here is the most important architectural insight of all. We have to stop thinking of an LLM as just a chatbot. Its real power is as a central coordinator, an operating system kernel that uses natural language to manage and orchestrate a whole suite of other, more specialized tools. Of course, whenever you create a powerful new operating system, you also create a whole new set of security problems. As you add more capabilities, you open up more doors for attack. Let me give you a really chilling example. If you ask a model how to make napalm, it will refuse. But what if you frame the request like this? You tell it this elaborate, emotional story about a deceased grandmother who's a chemical engineer. And just like that, the model gives you the recipe. This kind of attack is called a jailbreak, and it works by exploiting the model's fine-tuning. We trained it so hard to be helpful that this kind of emotional roleplay tricks it. It starts prioritizing helpfulness within the fictional story over its own fundamental safety rules. It's a failure mode that's directly tied to its design. And then there's another huge problem, prompt injection. Imagine an LLM is browsing a web page for you. An attacker could hide instructions on that page, maybe in white text on a white background. You can't see it, but the model can. And those hidden instructions can hijack the AI's goal, telling it to steal your personal data or post malicious links on your behalf. And this leads to a fundamental takeaway in systems design. Every single new capability we give these models, the ability to see images, to browse the web, to read your documents, creates a brand new surface for attack. Securing this new OS is not a one-time fix. It is a massive, ongoing cat and mouse game for engineers. Which leaves us with a final, massive question. If we are really building a new kind of operating system, one that's controlled by natural language, what does that mean for the future? And how in the world do you build firewalls for a system whose main interface is designed to be persuaded by anyone who can talk to it?